Welcome to today's deep dive. We're absolutely thrilled to have you with us today.
Because we are unpacking a topic that, honestly, it touches virtually every single aspect of your modern life.
Yeah, it really does. We are diving into a comprehensive 2026 resource today. It's titled Real-Time Artificial Intelligence: Key Motivations, Technologies, Platforms, and Use Cases.
It's quite a title.
It is, and it's a meticulously researched, highly technical compilation of insights from across the field. But look, our goal here isn't to just, read you a textbook.
No, absolutely not.
We want to take this incredibly dense material, strip away all the academic jargon, and translate it into a masterclass that you can actually use.
That is exactly the mission for today. Because if you've been following the tech space at all, you know the landscape is just littered with this alphabet soup of acronyms.
AI, ML, DL.
Exactly. We are going to completely demystify that hierarchy today. We'll explore the historical roots of these concepts, break down the specific algorithms powering the tech you use every day, and then
we're going to ground all of that theory in a massive real-world case study.
Right. We're going to examine how these exact systems are being deployed on the front lines right now to secure the global food supply by detecting plant diseases in agricultural fields.
I think that's the perfect way to approach this, because let's be honest, even when you understand the basics of technology, interacting with modern artificial intelligence can still feel like, pure magic.
It really can.
But when you dig into the foundational sources like we did for this deep dive, you realize it isn't magic at all. It's this fascinating, intricate mix of statistics, advanced pattern recognition, and essentially mathematical attempts to mimic the biological structure of the human brain.
Which is wild when you really think about it.
It is, and this deep dive is custom tailored specifically for you, for the listener who already has a grasp on the tech landscape but really wants to cut through the relentless hype cycle.
We want to bypass the science fiction.
Exactly. We want to understand exactly how these systems learn, how they make decisions, and why they fundamentally matter to your daily routine. Okay, let's unpack this.
To start unpacking it, we need to establish the foundational hierarchy, the structure of the entire field. And the most effective way to visualize this is by imagining 3 concentric circles.
Okay, like a bullseye.
Yeah, exactly like a bullseye. The largest outermost circle is artificial intelligence, or AI. AI is the broadest possible concept. It is simply the overarching endeavor to incorporate human-like behavior, reasoning, and intelligence into machines.
It's the ultimate end goal.
Right. Now, inside that large circle, you have a smaller, more specific circle, machine learning, or ML.
And machine learning is where we transition from just giving a computer a rigid list of rules to actually letting the computer figure things out on its own right.
Precisely. It's a specific subset of AI where machines learn from data and past experience. The whole goal is to automate the building of analytical models without needing a human programmer to sit there and explicitly write code for every single possible scenario.
Which would be impossible anyway.
Utterly impossible. And finally, inside that ML circle is the smallest, most intense core, deep learning, or DL.
The center of the bullseye.
Yes. Deep learning is a further specialized subset of machine learning that handles immensely complex computation through multi-layer neural networks, which we will definitely get into in detail later.
I really love having that mental map. It helps keep everything straight. And before we get into the heavy math of how those inner circles actually process data, we need to look at the historical timeline.
The history is fascinating.
It really is, because we have this tendency to think of machine learning as something invented in a Silicon Valley garage, like 10 years ago. But the roots go back decades. The source material highlights Alan Turing all the way back in 1948.
1948.
Yeah. Creating a paper and pencil chess game. Just think about the conceptual leap there. Computers of that era weren't even capable of running the program yet.
No, they barely existed.
Right. So Turing essentially played the role of the machine himself, calculating the algorithmic rules by hand.
It's a profound demonstration of how the theoretical desire to create AI vastly outpaced the physical hardware of the time. The brilliant minds of the mid-20th century, they knew exactly what they wanted to do. They just didn't have the silicon to do it yet.
Yeah. And following Turing, in 1952, you had Christopher Strachey developing a program to play the game of drafts, or checkers.
But the actual term machine learning wasn't officially coined until 1959.
By Arthur Samuel.
Who was another pioneer in computer gaming. He realized that if a computer could learn to play a game better than its creator, it was demonstrating a primitive form of learning.
Which is just incredible for 1959. But the development wasn't just a smooth upward trajectory from there, was it? The conceptual groundwork for neural networks, which is what powers today's deep learning, followed a really staggered, almost dramatic historical path.
It absolutely did. It was characterized by these massive bursts of optimism, followed by periods of just deep stagnation. For instance, in 1958, a researcher named Frank Rosenblatt demonstrated the perceptron.
The perceptron.
Yeah, which was an early, simplified attempt to model a biological neuron using hardware. And the initial excitement was palpable. Everyone thought they had cracked it.
But then progress essentially hit a brick wall.
A massive brick wall. In 1969, Marvin Minsky and Seymour Papert published highly influential work that rigorously highlighted the severe mathematical limitations of those early perceptrons.
Basically saying they couldn't solve certain complex problems.
Specifically, their inability to solve nonlinear problems.
Yeah.
And that publication effectively chilled research funding and interest for over a decade. It's a period the industry often refers to as an AI winter.
So what thawed it out? How did we get from that total dead end in the 70s to the systems we use today?
The thaw really began in 1986. A massive breakthrough occurred when Geoffrey Hinton and his colleagues successfully demonstrated a concept called backpropagation.
Okay, let me stop you there, because backpropagation comes up all the time in this space. Can you explain conceptually what that actually means for the network?
Absolutely. So imagine a network makes a prediction, and that prediction is wrong. In the early days, it was very difficult to figure out exactly which part of the multi-layered network was responsible for the error.
So you couldn't fix it.
Right. It was practically impossible to correct systematically. Backpropagation is a mathematical method that allows the network to calculate the gradient of the error and then literally propagate that error backwards through the layers of the network.
Hence the name.
Exactly. It essentially tells each individual artificial neuron, hey, here's exactly how much you contributed to this mistake, and here's how you need to adjust your internal settings so we don't make this mistake again.
Wow.
It allowed multi-layered networks to actually correct their own errors for the first time.
That sounds like the missing puzzle piece.
It was the theoretical missing piece, yes. But the modern explosion of deep learning didn't truly kick into high gear until around 2006.
Because they needed the hardware to catch up again.
Precisely. It required two modern catalysts to fully realize the potential of backpropagation. First, an absolute abundance of digital training data generated by the internet.
Right.
And second, sudden, massive leaps in computational power. Specifically, researchers started using graphics processing units, or GPUs, to handle the heavy math.
The same chips used for video games.
The exact same chips.
And all of that history leads us to how these machines actually learn today. The foundational material breaks machine learning down into three main paradigms.
Yes.
The first, and arguably the most common, is supervised learning. And I really appreciate the analogy used in the source here. It describes supervised learning like a professor supervising a student.
It's a great analogy.
You, the programmer or the professor, you feed the algorithmic student a giant set of labeled training data. The data consists of features, which are the measurable characteristics of the data, and labels, which are the correct answers.
Right.
So you show the student the features, tell them the correct label, and over time they learn to make the right predictions on novel data.
That's a great baseline. Now, within that professor-student dynamic, supervised learning is generally divided into two distinct types of mathematical problems: classification and regression.
Right, so classification is exactly what it sounds like, putting things into distinct buckets or categories.
Correct. Classification is for discrete categories. It's binary or multi-class sorting. So, for example, sorting data into red versus blue, or analyzing a financial transaction as fraudulent versus legitimate.
Or looking at a medical image and deciding disease versus no disease.
Exactly. Regression, on the other hand, deals with predicting continuous numerical values.
So not a bucket, but a sliding scale.
You use regression when you want to predict things on a spectrum, like forecasting a dollar amount for a housing price based on square footage, or predicting the future weight of an object.
And to solve these two types of problems, there is a whole toolbox of specific supervised algorithms mentioned in the text. Let's walk through a few of the major ones. Linear regression seems to be the most foundational.
It is. Linear regression attempts to model the relationship between two variables by fitting a straight line to the observed data. It is simple, but it is highly effective for straightforward continuous predictions.
Okay.
Then you have logistic regression, which, despite having the word regression in its name, is actually a workhorse for binary classification tasks.
Oh, interesting.
Yeah, uses a logistic function to model a binary dependent variable. For instance, determining the probability that an email is spam or not spam, and then assigning it to a category based on that probability.
Okay, those are the smoother mathematical curves. But what if the data doesn't fit a neat curve? What if it's more about making a series of distinct choices? That brings us to decision trees.
Yes.
I've always visualized these as literally building a hierarchical tree-like structure of yes or no questions.
That is exactly how they operate. A decision tree splits the data based on feature values. So it asks, is the income over $50,000? Yes or no?
And then it branches.
It keeps branching down based on those conditional splits until it reaches a final conclusion at the leaves of the tree. They are incredibly intuitive and easy to interpret. But there is a vulnerability here.
Which is?
A single decision tree can easily become overly complex and literally memorize the specific quirks of the training data. It's a problem known as overfitting.
And the solution to a weak individual tree is to build a whole forest, right? Hence, random forests.
Exactly. A random forest is what we call an ensemble method. Instead of relying on one super complex tree that might memorize the data, it creates a whole multitude of different, slightly randomized decision trees.
It builds an entire forest.
It has all of them independently analyze the data, and then it aggregates the predictions, essentially taking a democratic vote for a final, highly accurate, much more robust answer.
I understand the branching logic of trees, but what happens when the data is incredibly complex and plotted out in multiple dimensions? You can't just draw simple yes or no boxes around it.
No, you can't.
This is where support vector machines, or SVMs, come into play in the text.
SVMs are fascinating. Imagine you have two distinct classes of data points scattered on a graph, and you need to draw a line to separate them. But not just any line. You want the best possible line.
Right.
SVMs work by finding the optimum hyperplane, which is essentially a complex mathematical boundary in high-dimensional space. The goal of the SVM is to maximize the margin, or the empty space, between the hyperplane and the closest data points from both classes.
It's like trying to build the widest possible street separating two distinct neighborhoods.
That's a perfect way to look at it. By maximizing that margin, the model becomes much better at classifying new, unseen data.
That makes perfect sense. And to round out the supervised toolbox, there is naive Bayes.
Yes, naive Bayes is fundamentally different from the others because it relies purely on probability. Specifically Bayes' theorem. It calculates the conditional probability of a data point belonging to a certain class based on its features.
Why is it called naive?
The reason it is called naive is that it makes a massive underlying assumption. It assumes that all the features are completely independent of each other, which is rarely true in the real world.
Right, things are usually connected.
Yet, despite this naive assumption, it performs surprisingly well, especially in text classification and spam filtering.
Okay, so that covers the supervised side, where the algorithm is guided by clear labels from the professor. But what happens when you don't have a professor? What happens when you just have a massive, chaotic pile of data and no labels whatsoever to tell the machine what it's looking at?
That leads us to the second major paradigm, unsupervised learning.
Right.
In unsupervised learning, the algorithm is entirely on its own. It must explore the data and find hidden structures, patterns, and relationships without any prior guidance. There are two primary techniques utilized here.
Okay, what's the first one?
The first is clustering. Without knowing what the data points represent, the algorithm analyzes their inherent features and groups items that have maximum similarities into distinct clusters. It discovers the natural groupings within the data.
So if you fed it 1 million unlabeled photos of vehicles, it might group all the two-wheeled objects into one cluster and all the four-wheeled objects into another simply by recognizing the shared pixel pattern.
Without ever knowing the words motorcycle or car.
Exactly.
Precisely. The second major technique is association rules. This is less about grouping things and more about finding sequential relationships in massive databases.
The classic example being the grocery store, right?
Yes, market basket analysis. The algorithm combs through millions of grocery store receipts to discover that customers who buy diapers are also highly likely to buy beer on the same trip.
Which is wild.
But it's true. It finds these hidden, actionable correlations that humans might completely overlook because we wouldn't think to look for that connection.
Which brings us to the third paradigm, reinforcement learning, or RL. Of the three, this one always feels the most like a video game to me.
It's a very apt comparison. In reinforcement learning, the terminology shifts entirely. You have an agent interacting within a specific environment.
Okay.
The agent isn't given labeled data, nor is it just looking for clusters. Instead, it is dropped into the environment with a specific goal and told to figure out how to achieve it from scratch.
So how does it actually learn what to do? If there's no data telling it the rules, isn't it just flailing around randomly?
Initially, yes, it explores randomly, but the learning mechanism is a beautifully elegant system of trial and error. The agent observes the current state of the environment and takes an action.
And then what?
Depending on the outcome of that action, the environment provides immediate feedback in the form of a numerical reward or a penalty. The core of this process involves updating what are called Q values.
Use values.
You can think of a Q value as the agent's internal estimate of how good a certain action is given a certain state.
So if it touches something hot, the Q value for that action in that state drops drastically because of the penalty.
Right.
But if it finds a shortcut to the goal, the Q value skyrockets because of the reward.
Exactly. The overarching objective of the agent is to maximize its cumulative reward over time. It has to constantly balance exploration, trying new, random things to see if they yield higher rewards with exploitation.
Exploitation meaning just doing what it already knows works.
Using the actions it already knows will yield a reliable reward. The literature specifically references robust training algorithms like Q-learning and SARSA that meticulously manage this trial and error optimization, allowing the agent to eventually master incredibly complex environments.
So tying this vast foundation back to you, the listener, and your daily life, you might not realize it, but these three paradigms are constantly running in the background of your day.
All day, every day.
Supervised learning is the algorithm currently guarding your email inbox, instantly filtering out spam because it was trained by a programmer on millions of explicitly labeled examples of malicious emails. Unsupervised learning is the silent engine behind your favorite streaming service, recommending your next movie by clustering your viewing habits with millions of other users without ever needing a human to label your specific taste profile.
Yep.
And reinforcement learning. That is exactly how the self-driving cars you see testing on the highways are trained to navigate dense traffic. They act as digital agents learning to maximize the reward of smooth, safe driving while heavily penalizing the parameters that lead to crashes.
That is a perfect summation of the traditional machine learning landscape. But if we connect this to the bigger picture, we have to move beyond these broader algorithms. We need to transition into the core focus of modern AI capabilities.
Deep learning.
Deep learning. This is where we move from statistical sorting to attempting to literally mimic the structural architecture of the human brain.
And this is exactly where the technology starts to feel a bit intimidating, because this is the stuff that makes the global headlines.
It is.
Deep learning essentially abandons those simpler linear models, those single decision trees, and builds incredibly complex interconnected networks of artificial neurons or nodes. And the architecture of these networks is fundamentally brilliant in its design.
It is a layered approach to processing information. To visualize it, you start with an input layer. This layer's only job is to take in the raw, unrefined data.
Like what?
For instance, the individual pixel values of a digital photograph or the audio frequencies of a spoken sentence. That raw data is then passed into what are known as the hidden layers.
And the hidden layers are where the actual magic happens, right? This is where the network figures out what it's looking at.
Yes, the hidden layers are the engine of deep feature extraction. In a standard network, you might have dozens or even hundreds of these hidden layers stacked on top of each other.
Just a massive stack of neurons.
The data flows through these layers, being mathematically transformed at each step, until it finally reaches the output layer, which delivers the final decision or classification.
Like outputting the word cat if the input was a picture of a feline.
Exactly.
But to really understand how the information transforms as it flows from the input to the output, we have to look at the connective tissue of the network. The source material highlights two absolutely critical components here: weights and activation functions.
Inertial components.
I think we all have a vague idea of what a weight is in a network, but how does it actually function?
Think of the network as a massive web of connections between all these artificial neurons. Those connections are governed by weights. A weight is simply a numerical value that determines the robustness or the relative importance of a specific connection between two neurons.
Okay.
As the network learns, say, via that backpropagation method we discussed earlier, it is constantly tweaking and adjusting millions of these weights to minimize its error rate. It learns which pathways are important for a correct answer and which are totally irrelevant.
But if you just multiply the inputs by a bunch of weights, no matter how many layers you have, mathematically, you still just end up with one giant linear equation, a straight line. And the real world isn't a straight line.
That is the crucial insight, and that is exactly why activation functions are mandatory. An activation function is a mathematical operation applied to the output of a neuron before it passes the signal to the next layer.
And what does it do?
Its primary purpose is to introduce nonlinearities into the system.
Can you give an example of how that works in practice?
Certainly. A common activation function is the ReLU, or rectified linear unit. It's surprisingly simple. If the input is positive, it passes it through unchanged.
Okay.
If the input is negative, it outputs 0.
That simple kink in the math, that nonlinearity, prevents the network from collapsing into a simple linear regression model?
Wow, just by turning negatives to 0. It's elegant. By applying functions like ReLU, or the S-shaped sigmoid, or tan at the node level across thousands of neurons, the network gains the immense expressive power required to learn incredibly complex, nuanced, and chaotic real-world patterns.
Okay, so we have this foundational structure. Input, hidden layers of weighted neurons, nonlinear activation functions, and output. But just like in the animal kingdom, evolution has taken that basic structure and created a whole menagerie of different deep learning algorithms.
It really has.
Each one is highly specialized and evolved for a specific type of data environment. Let's start with the undisputed heavyweight champions of visual data, CNNs, or convolutional neural networks.
CNNs completely revolutionize computer vision. They are specifically tailored to process grid-like structured data.
Which perfectly describes how the pixels in a photograph or a frame of video are arranged.
Precisely. Instead of just looking at a chaotic jumble of pixels, a CNN preserves the spatial relationships in an image. It does this through a highly specific architectural pipeline.
Right, and it starts with the convolutional layers. How do those actually look at the image?
Imagine taking a small, square magnifying glass and slowly sliding it across a photograph, row by row, column by column. In a CNN, that magnifying glass is called a filter or a kernel.
A kernel.
Yes. It is a small matrix of weights that slides or convolves across the image. As it slides, it performs mathematical dot products, essentially looking for specific local patterns.
Like what kind of patterns?
The earliest layers might just have filters that look for vertical edges or horizontal lines.
Okay.
The next layer takes those edges and looks for corners. The next layer combines corners into shapes. It's a hierarchical extraction of visual features.
But if you're sliding a filter across every single pixel of a high-resolution image, the amount of data generated must be astronomical. How does the network not just crash under the weight of the computation?
That is where the second major component comes in, pooling layers. Pooling is a downsampling technique. After a convolutional layer extracts the features, the pooling layer reduces the spatial dimensions of the data.
Shrinking it down.
Exactly. For instance, max pooling might look at a 2x2 grid of pixels and only keep the single highest value, discarding the rest. It aggressively compresses the data while retaining the most essential dominant features, which makes the computation manageable.
And then what happens to that compressed data?
Finally, after passing through multiple convolutions and pooling layers, the condensed feature-rich data flows into traditional fully connected layers to make the final classification. As a historical note, Jan LeCun pioneered this specific architecture with his Linnet model in 1998.
1998.
Yeah, which was originally deployed to automatically read handwritten zip codes on mail.
Here's where it gets really interesting. CNNs are incredibly powerful for a static grid-like image, but what if your data isn't a static snapshot?
Right.
What if it is a sequence unfolding over time, a sentence of text, a snippet of a conversation, or a time series of fluctuating stock prices? A CNN doesn't handle time very well.
Not at all.
That is where RNNs, or recurrent neural networks, enter the picture.
Precisely. RNNs are designed specifically to process sequential data. They achieve this by utilizing internal feedback loops. Unlike a CNN or a standard feed-forward network, where the data strictly flows in one direction from input to output, an RNN has connections that allow information to loop back on itself.
So it essentially has a memory.
Exactly. It maintains an internal state or context of past inputs. When an RNN is processing a word in a sentence, it isn't just looking at that word in isolation. It is actively considering the hidden state generated by the words that came immediately before it.
It understands sequence.
It does. However, standard RNNs suffer from a debilitating mathematical flaw known as the vanishing gradient problem.
Which goes back to that backpropagation we talked about. If the network is trying to learn from a mistake at the end of a long sequence, it has to send the error signal all the way back to the beginning.
Yes. And because it uses the chain rule of calculus, it has to multiply gradients together over and over again. If those gradients are fractions, numbers less than 1, multiplying them repeatedly causes the value to shrink exponentially until it literally vanishes.
The error signal just fades away.
The result is that standard RNNs essentially suffer from amnesia. They tend to completely forget information from early in a long sequence. To solve this critical flaw, researchers developed a highly specialized variant of the RNN called LSTMs, or long short-term memory networks.
I found the description of LSTMs in the source material absolutely fascinating. They possess this complex chain-like structure with 4 interacting neural network layers within each repeating module. And the absolute key to their success is a brilliant mechanism called forget gates.
The forget gate is a masterclass in network efficiency. Instead of just cramming every piece of new sequential information into its memory state, the LSTM uses the forget gate, which is typically powered by a sigmoid activation function, to actively evaluate the incoming data against the historical context.
And it makes a choice.
It assigns a value between 0 and 1. A 0 means completely discard this irrelevant piece of history, and a 1 means this is vital context, keep it.
It's like having a highly efficient executive assistant constantly managing your memory. If you're reading a paragraph and the subject changes from a dog to a car, the forget gate flushes the dog context so you don't get confused, ensuring you don't get overwhelmed by a long sequence of data.
It is an incredibly powerful, robust architecture for time series and natural language. But moving on from sequences, let's look at a completely different capability. Generation.
Oh, this is the fun stuff.
The deep learning section dedicates significant space to a revolutionary architecture known as GANs, or generative adversarial networks. A GAN is fundamentally different from what we've discussed so far. It is essentially a 2-player mini-maxed game played continuously between 2 entirely distinct neural networks, a generator and a discriminator.
I mean, this genuinely sounds like the plot of a sci-fi thriller. 2 AI networks battling it out. How does this game actually function mathematically?
It begins with an input noise vector, which is essentially a string of random mathematical static, usually denoted in the literature as Z.
Just static.
Pure noise. This random noise goes into the first network, the generator. The generator's sole purpose is to try and sculpt that random noise into synthetic data that looks completely real.
For instance, generating a fake photograph of a human face.
All right. This synthetic output, mixed in with actual real photographs of human faces, is then fed to the second network, the discriminator.
The opponent.
The discriminator's entire job is to act as a forensic detective. It analyzes the images and attempts to calculate the probability that the image is a fake.
And they just lock into this relentless battle. The generator analyzes where it failed and keeps trying to create better, more nuanced fakes to fool the discriminator. Meanwhile, the discriminator learns from its mistakes and keeps getting better at spotting the microscopic, pixel-level flaws in the fakes.
Precisely. They train simultaneously, locked in an adversarial loop, pushing each other to improve. The process continues until it reaches an equilibrium.
Meaning what, exactly?
Ideally, a point where the generators become so incredibly proficient that the synthetic data it produces is completely indistinguishable from reality, and the discriminator is essentially reduced to guessing at random.
Flipping the coin.
Exactly. The applications are massive. This is the exact underlying technology used to create deepfakes, but it's also heavily utilized in creative industries. For example, the video game industry uses GANs extensively to take older, low-resolution 2D graphics and intelligently scale them up to hyper-realistic 4K resolutions by generating the missing pixel detail.
It's astounding. And while GANs are generating new data, there is another architecture discussed that does the exact opposite. It squashes data down. Let's talk about the autoencoder.
Unlike GANs, an autoencoder is primarily an unsupervised model. Its main applications are data compression, dimensionality reduction, and denoising images. The architecture of an autoencoder consists of 2 symmetrical parts. First, you have the encoder. The encoder takes high-dimensional input data, like a highly detailed image, and systematically squashes it down through progressively smaller hidden layers until it reaches a low-dimensional representation. This central compressed point is called the latent space, or the bottleneck.
So it's forcing a massive amount of information through a tiny pipe.
Exactly. Then, the second part, the decoder, takes over. The decoder takes that highly compressed representation from the bottleneck and attempts to perfectly reconstruct the original high-dimensional input data.
But why go through that process just to get the same image back? It seems redundant.
Because by forcing the data through that strict bottleneck, the network is unable to just memorize the image pixel by pixel. It is mathematically forced to learn only the most salient, absolute essential features of the data needed to rebuild it.
Oh, I see.
Consequently, it naturally filters out all the irrelevant background noise. When you reconstruct the image from the bottleneck, you get a clean, denoised version of the essential data.
That is brilliant. The resource we are exploring is just packed with these diverse architectures. It also covers several others that I think we should at least touch upon to show the breadth of the field. It mentions RBFNs, which use radial basis functions and Gaussian transfer functions, making them highly effective for certain types of time series estimation and function approximation.
Yeah.
It details MLPs, or multi-layer perceptrons, which are your standard bread and butter feed-forward networks, utilizing those ReLU and sigmoid activations we unpacked earlier.
And we also see SOMs, or self-organizing maps, originally created by Tuvo Kohonen. SOMs are unique because they use competitive learning rather than error correction learning. They are fantastic for visualizing high-dimensional data on a 2D map by constantly updating weights to find what is called a best matching unit, or BMU, for a given input.
Best matching unit, okay.
And finally, the text discusses RBMs and DBNs, restricted Boltzmann machines and deep belief networks. These are another Jeffrey Hinton creation. They use visible and hidden layers along with a complex probabilistic technique called Gibbs sampling.
Gibbs sampling.
Essentially, Gibbs sampling allows the network to approximate complex joint probability distributions by iteratively sampling from simpler conditional distributions. It's a way for the network to find the most probable, stable state of the data.
If we step back and connect this to the bigger picture, reading about all these varied architectures, CNNs convolving over pixels, LSTMs managing memory sequences, GNs battling each other, and Gibbs sampling it can easily feel intensely abstract.
Like it's just theoretical math happening in a server room somewhere.
Exactly. But the second part of our exploration today radically grounds all of this theory. It takes these exact deep learning models and applies them to a massive, highly critical, physical, real-world problem, securing the global food supply by detecting plant diseases out in agricultural fields.
If we connect this to the bigger picture, this is where the theoretical stakes become incredibly tangible. We are talking about global food production, food security, and the economic survival of farmers worldwide.
Huge stake.
Historically, if a farmer walked their field and noticed a crop starting to turn yellow or developing strange necrotic spots, the diagnostic pipeline was incredibly slow. The only reliable way to diagnose the specific disease was a visual inspection by a highly trained human expert in plant pathology.
And as you can imagine, those PhD-level human experts are incredibly rare. They can't be everywhere at once. And even they are subject to human error and fatigue when you ask them to look at thousands of slightly different leaves across acres of farmland.
They're human.
Now, we are seeing the architectures we just discussed, machine learning and deep learning, being deployed to completely automate and democratize this vital diagnostic process.
But just like we discussed with the professor and student analogy earlier, an AI is only as good as its training data. To train these complex computer vision systems to act as master botanists, researchers need massive, meticulously verified datasets of labeled images.
They need millions of flashcards.
Yes. The source text highlights two major foundational datasets that have driven this specific agricultural research. The first is known as the Plant Village dataset. This is a massive, widely used open access repository containing over 50,000 high-resolution images. It's broad, covering 14 different crop species and 26 distinct diagnosed plant diseases.
It's the standard encyclopedia for the AI.
Yes, and the second is the cassava leaf disease dataset, which takes the opposite approach, extreme specialization.
Just focusing on one plant.
It contains 21,000 labeled images, focused entirely on the various viral diseases and deficiencies afflicting just the cassava plant, which is a crucial staple crop for millions of people.
But the challenge isn't just acquiring the photos. You can't just take a raw, high-resolution photo straight from a smartphone in a muddy field and shove it directly into an algorithm. The raw data is inherently messy.
Very messy.
You have harsh glare from the sun, weird shadows from other plants, and digital noise from chip camera sensors. So before the AI even sees the image, researchers have to run it through a rigorous pipeline called pre-processing.
Pre-processing is absolutely vital for accuracy. The first major step often involves color space conversion. A standard digital photo is in RGB format, red, green, blue. But RGB is highly susceptible to variations in lighting. A shadow changes the red, green, and blue values simultaneously.
So it throws the whole color off.
Yeah, so researchers often mathematically convert the image from RGB into alternative color spaces like HSV hue, saturation, value, or LAB.
Why LAB? How does that actually help the AI?
The LAB color space separates the image's lightness, the L, from the actual color information, the A and B. By separating the lightness out entirely, researchers can effectively neutralize the impact of harsh shadows or uneven sunlight on the leaf.
So the AI just sees the true color.
Presenting the AI with a much purer representation of the leaf's actual color pigments. After color conversion, they apply mathematical smoothing filters. Specifically, Gaussian or median filters are used to blur out the microscopic digital background noise without destroying the sharp edges of the disease spots on the leaf.
And then there's a technique that I find incredibly clever, data augmentation. Because getting 50,000 photos is hard, researchers artificially multiply their data set.
They create more data out of thin air.
So they take a single image of a diseased leaf, and they use software to flip it horizontally, rotate it 45 degrees, stretch it, warp it, and change the brightness. To a human, it's obviously the exact same leaf.
Right.
But to the pixel analyzing algorithm, each variation looks like a completely new, unique piece of training data. It simulates the infinite variations of the real world and prevents the model from just memorizing the exact orientation of the original photos.
Once you have this beautifully clean, augmented data set, we see a fascinating historical divide in the research. A paradigm shift between traditional machine learning methods and modern deep learning methods. This perfectly illustrates why the field moved toward deep neural networks.
Okay, let's look at the old way first.
In traditional machine learning, researchers had to perform a labor-intensive process called manual feature extraction.
Right, the AI couldn't just look at the leaf and figure out what mattered.
Yeah.
The humans had to tell it exactly what mathematical properties to measure.
Exactly. Researchers had to physically write complex algorithms to calculate specific, isolated attributes of the diseased leaf. For example, they would extract color features. To isolate the disease spot from the healthy green leaf, they would use techniques like Otsu's thresholding, which mathematically calculates the optimal pixel value to separate the foreground from the background. Once isolated, they wouldn't just look at yellow. They would calculate the statistical skewness and kurtosis of the color distribution.
Okay, let's break that down, because kurtosis is a heavy statistical term. How do you calculate the kurtosis of a leaf spot?
Imagine plotting all the pixel colors of the disease spot on a bell curve graph. Skewness measures whether the curve leans to the left or right. Kurtosis measures the tailedness or the sharpness of the peak of that curve.
So does the color variation form a tall, sharp spike, or is it a flat, wide mound?
Exactly. It's a highly specific mathematical representation of the color variation. But color wasn't enough. They also had to calculate shape features, writing code to trace the total perimeter of the spot or calculate the geometric eccentricity, determining if the spot was a perfect circle or a stretched oval.
Wow.
And finally, they would calculate texture features.
Texture from a 2D photo, how is that even possible?
Yes, using incredibly complex statistical tools like the gray level co-occurrence matrix, or GLCM. The GLCM basically analyzes how often pixels of certain brightness levels appear next to each other, mathematically quantifying whether the surface of the leaf looks smooth, rough, or mottled.
That sounds absolutely exhausting to program. But to be fair, it worked. The source material highlights a specific success story of this traditional manual method. A comprehensive study focused on diseases affecting rice leaves.
The rice leaf study.
The researchers painstakingly manually extracted 172 distinct color features across 13 different color spaces. They took all 172 of those hand-calculated mathematical values and fed them into an SVM classifier, that support vector machine algorithm we discussed earlier, looking for the optimal hyperplane. And they achieved an incredible 94.65% diagnostic accuracy.
It was a triumph of statistical engineering, but there was a fatal, crippling catch to this traditional methodology. It required human intervention at the bottleneck.
Right.
To calculate those 172 features accurately, researchers had to manually digitally crop the diseased portions out of every single training image and testing image during pre-processing to remove the background soil and stems. It was not a fully automated pipeline.
And that bottleneck is precisely why the entire field of computer vision shifted so rapidly and aggressively toward deep learning. Deep learning models, specifically those CNNs we broke down earlier, entirely bypass that tedious manual feature extraction process. Because of those dozens of hidden layers, a CNN acts as an automated feature extractor.
It's a fundamental paradigm shift. You don't tell the CNN to look for kurtosis or perimeter eccentricity. You just feed it the raw, uncropped pixels. And through the process of convolution and backpropagation, the network automatically learns which combinations of color, shape, and texture matter most for the diagnosis.
It does the heavy lifting for you.
It figures out the optimal identifying features entirely on its own, without a human ever having to manually crop the background or write a GLCM algorithm.
And the specific triumphs of deep learning in this agricultural space are staggering. The textbook details several specific models achieving results that eclipse the manual methods. Researchers took the famous AlexNet architecture, which is a relatively early CNN that utilizes 8 distinct layers and features roughly 60 million tunable parameters, or weights. And they trained it specifically on the tomato leaf subset of the dataset. It hit an astonishing 97.29% accuracy entirely on its own.
And as computational power grew, so did the depth of the networks. Another team utilized a much deeper, more complex model called VGG16. As the name implies, it has 16 weight layers totaling 23 layers overall and boasts an enormous 138 million parameters.
138 million.
They unleashed this massive architecture on the problem and bumped the accuracy up to 97.49%. We also see highly specialized, custom-built CNNs targeting specific crops. A study designed a CNN to identify cucumber diseases, specifically looking to differentiate between 2 complex viral infections, the MYSV and ZYMV viruses, and hit a 94.9% accuracy rate without any manual feature engineering.
I want you, the listener, to just pause and think about what that shift actually means for a moment. Imagine you are an agricultural researcher or a desperate farmer trying to manually write code to calculate the kurtosis or the geometric eccentricity of a single tiny yellowing spot on a single leaf.
It would take hours.
Hours of tedious coding. Contrast that with handing thousands of raw, uncropped photos directly to a convolutional neural network that automatically slides its filters over the pixels and maps out the exact mathematical pattern of the viral infection in a matter of fractions of a second. This is the sheer raw power of automated AI being leveraged to save crops and secure the human food supply.
It sounds like an unequivocal utopian victory for technology. But what makes this deep dive truly valuable is that we are looking at the friction. The source material doesn't pull any punches. It dedicates a significant amount of critical analysis to the unresolved issues and the massive bottlenecks in the technology. Because while 99% accuracy sounds phenomenal when published in a controlled laboratory paper, reality out in the dirt is much, much messier.
And that leads us to the biggest, most glaring issue: data limitations and the inherent bias of the training data sets. Let's look at why that perfect lab data actually creates a massive blind spot for the AI.
It comes down to a massive disconnect between laboratory conditions and field conditions. Let's look at the gold standard, the Plant Village dataset. The vast majority of those 50,000 images were captured in highly controlled environments. An expert took a single diseased leaf, placed it on a perfectly uniform, solid gray or black background, and photographed it under consistent, balanced artificial laboratory lighting. It's pristine data.
But out in the real world, a leaf isn't sitting on a gray mat in a studio. It's attached to a swaying plant, surrounded by other overlapping green leaves, with complex brown soil in the background, half cast in harsh sunlight and half in deep shadow.
Exactly. And getting thousands of high-quality, perfectly labeled images of leaves in those chaotic field conditions is prohibitively expensive. It requires sending actual agricultural experts out into the mud to find the diseases, photograph them in the wild, and individually verify the diagnosis to label the data. Consequently, most models are trained almost exclusively on the pristine lab data.
And this leads to what is arguably the most shocking, crucial statistic in the entire analysis. We call it the real-time drop-off. One research team trained a highly sophisticated model strictly on that clean laboratory data, and it hit an incredible 99.35% diagnostic accuracy. It seemed perfect.
It really did.
But then they took that exact same highly trained model and deployed it on a new data set of real field images with those complex backgrounds of soil and other plants we just described. The accuracy didn't just dip, it plummeted catastrophically to just 31%.
It's a phenomenon somewhat akin to the clever Hans effect in psychology. Clever Hans was a horse that supposedly could do math, but was actually just reading the unconscious body language of his trainer.
The AI was doing the same thing.
In this case, the AI hadn't actually learned the complex, nuanced visual pattern of the disease itself. Without anyone realizing it, the AI had learned to rely heavily on the visual contrast provided by the pristine, uniform gray background to make its diagnosis. When that clean background was removed and replaced with chaotic visual noise, the AI's internal logic totally collapsed. It failed completely.
Furthermore, even if you solve the background issue, you have the profound biological complexity of the diseases themselves. Out in the real world, diseases don't present in a vacuum. You have the severe issue of visual similarity across multiple diseases.
Biology is wildly inconsistent. The physical symptoms of a fungal infection can change drastically based on the local geography. Subtle shifts in weather patterns, the specific humidity levels of the week, and the specific growth stage of the crop. A disease looks different on a seedling than it does on a mature plant.
And even worse, for a single label classification model, a plant might be suffering from two distinct problems simultaneously. A single leaf might be infected with two different fungal diseases at the exact same time, creating a blended, chaotic symptom pattern. Or it might have a viral disease that is visually complicated by a simple nutritional deficiency in the soil, like a lack of nitrogen causing the whole leaf to yellow. These overlapping compound symptoms utterly confuse models that were rigidly trained to only identify one pristine disease per image.
Beyond the biological chaos, there is a massive hardware and infrastructure bottleneck. We have to look at the computational costs versus the desperate need for lightweight models. We've spent a lot of time praising the immense power of these deep, multi-layered networks, but that analytical power comes at a literal physical cost. Models like Inception ResNet v2, which is a massive architecture, highlighted in the text that boasts 572 distinct layers and takes up roughly 215 megabytes of storage space.
That's huge for a single model.
Or that VGG16 model with its 138 million mathematical parameters. They require massive, dedicated GPU power and huge amounts of RAM simply to run a single image through the network.
You can't just run an Inception model on a standard processor, but the end user for this agricultural AI isn't a computer scientist sitting in an air-conditioned server room with a supercomputer. The target user is a farmer standing in the middle of a 200-acre field, likely holding an older smartphone, with absolutely zero reliable cellular internet connection to bounce the image to a cloud server.
Precisely. If the technology can't reach the edge, the actual location where it's needed, it's useless. Therefore, there is a desperate ongoing race in the engineering community to develop what the industry calls lightweight deep learning models. The goal is to aggressively compress the neural architecture without sacrificing too much accuracy. The text highlights several specific lightweight architectures designed to solve this exact bottleneck. You have models like SqueezeNet, which uses brilliant architectural tricks to compress a highly accurate model down to an incredibly small footprint of just 5 megabytes. Or MobileNet v2, which operates at roughly 14 megabytes.
So these highly compressed models are engineered to be downloaded once and then run entirely locally on a standard low-power mobile phone processor without ever needing cloud computing or an internet connection. You sacrifice a tiny fractional bit of theoretical laboratory accuracy in exchange for massive, real-world practical utility.
But even if you get the model successfully compressed and running instantly on a farmer's phone, you still run headfirst into a massive philosophical and practical hurdle: the black box problem and the inherent danger of overfitting.
This goes back to why deep learning replaced manual feature extraction. Because the hidden layers extract their own features, they completely lack human interpretability.
Exactly. If a traditional SVM model makes a decision, a researcher can look at the 172 features and see exactly which mathematical value triggered the result. But a deep neural network is a black box. If the AI analyzes a photo and tells a farmer they need to preemptively destroy an entire acre of crops to stop a highly contagious blight, the farmer naturally wants to know why. What specific pattern did you see? But the network can't easily explain its internal logic in human terms. It just outputs a probability percentage based on millions of incomprehensible weight calculations.
And The danger is that the black box might be suffering from overfitting, meaning it just memorized the training data rather than actually learning the generalized underlying rules of the disease. If it overfits, it might be giving catastrophic, crop-destroying advice based on a completely irrelevant detail it memorized, like the specific angle of the sun in the training photos or a specific type of dirt in the background. It's a massive trust issue.
This brings us to a crucial pivot in our broader understanding. We spend a significant amount of time looking deeply at the agricultural sector because it provides such a clear, tactile example of the stakes. But it is vital to recognize that these exact same deep learning algorithms, built on these exact same architectures and facing these exact same black box and dataset challenges, are deeply embedded everywhere.
So what does this all mean? Let's pivot right back to your everyday world, pulling rapidly from the broader applications covered in the text to see how this incredibly complex math permeates your daily life. Let's walk through a theoretical day in the life of AI.
It starts the moment you wake up, grab your phone, and begin your morning commute. When you pull up Google Maps or Waze, you aren't just looking at a static map. You're actively utilizing reinforcement learning and complex time series data analysis. The system's digital agents are constantly evaluating historical traffic congestion data against real-time sensor inputs from millions of other phones, constantly recalculating Q values to optimize your specific routing and maximize the reward of a shorter commute. And if you have an issue with your transit pass or a service during the morning and interact with the customer service window, the chatbots that are increasingly resolving those issues instantly are driven by advanced natural language processing models built on deep recurrent neural networks.
Then you arrive at work, and the entire global financial sector running in the background of your job is completely dominated by this tech. The literature notes that high-frequency algorithmic trading firms use those exact same LSTMs, the sequential networks, the forget gates that we discussed earlier, to rapidly analyze and react to micro-fluctuations in stock market values in real time, executing trades faster than a human could ever blink. And on a more personal level, every time you buy a coffee or lunch, payment platforms like PayPal are deploying massive predictive data analysis models to catch unauthorized transactions. In fact, the text highlights a specific metric. By utilizing deep sequential behavioral analysis, analyzing the sequence of how and where you typically spend money, not just the single transaction platforms have improved their fraud detection accuracy by up to 10%, silently keeping your money safe behind the scenes.
And when the workday ends and you come home to relax, the entertainment and media sectors take over your digital interaction. E-commerce giants like Amazon and streaming services like Netflix rely on intricate, unsupervised learning and complex clustering models to highly personalize your product and viewing recommendations, constantly finding hidden associations in your behavior. But it goes far beyond just recommending existing media. Generative AI is actively creating it. Deep learning architectures like WaveNet and Music 21 are currently capable of generating entirely synthetic raw audio and composing original music tracks that mimic human emotion.
We even see generative models like Chromagan being deployed to automatically colorize century-old black and white family photos. And it doesn't just guess the colors. It uses its convolutional layers to analyze the semantic context of the image, recognizing that a specific texture is grass or a specific shape is the sky, and applies the historically accurate colors. And simultaneously, while you're scrolling, other deep learning models are constantly scanning your social media feeds, acting as digital discriminators, attempting to filter out fake news and artificially manipulated media generated by adversarial networks.
But perhaps the most profound, consequential applications mentioned in the comprehensive overview are found in healthcare. We're talking about deep learning models powering advanced 3D imaging software to accurately locate and map brain tumors from MRI scans, drastically reducing human error in critical surgical preparation. And one of the most remarkable examples highlighted involves MIT researchers who are actually using deep learning to analyze subtle behavioral and vocal patterns to detect speech, language, and cognitive developmental delays in infants before they even hit kindergarten age.
That is incredible. They're completely bypassing the need for slow, highly subjective manual parental surveys, allowing for objective, early medical intervention that can quite literally change a child's entire life trajectory.
It is truly a breathtaking scope of application. The fundamental mathematics of pattern recognition are reshaping every single industry.
As we wrap up today's deep dive, I just want to take a second to recap the sheer distance we've covered in this discussion. We started all the way back with Turing's paper computer and Arthur Samuel officially defining the concept of machine learning in 1959. We walked through the rigid math of supervised and unsupervised learning paradigms and the fascinating trial and error video game of reinforcement learning. We ventured into the complex hidden layers, weights, and activation functions of convolutional neural networks and LSTMs that attempt to replicate the structural architecture of our own biological brains. We saw those powerful networks deployed directly on the muddy front lines of global agriculture, attempting to secure our food supply by automating the diagnosis of diseased leaves, and then we traced those exact same underlying algorithms right back to the traffic apps, the fraud detectors, and the medical scanners you interact with every single day.
This raises an important question, though, and it's something we must consider as this technology scales. Throughout this deep dive across every paradigm in architecture, we have seen a recurring, unavoidable theme of friction and fragility. We've successfully built incredibly complex, mathematically beautiful systems that can diagnose a failing crop, predict the subtle fluctuations of the stock market, or compose a symphony by mimicking our brain's architecture. But as the research rigorously points out, with that staggering 31% real-time drop-off, these systems still struggle immensely and often fail entirely when the environment changes even slightly. An AI that operates with 99% accuracy in a sterile lab can become entirely useless simply because a leaf is photographed in natural dappled sunlight rather than under a perfectly balanced fluorescent bulb. They lack human common sense.
And that fragility leads to a provocative thought I want to leave you with today. As you go through your day tomorrow, look closely at the personalized recommendations on your screens, the optimized traffic routes guiding your car, and the automated tools you rely on to do your work. If these deep neural networks are constantly learning, constantly updating their millions of weights, and constantly rewriting their own internal rules based strictly on the immense volume of data we feed them, what happens when the majority of the data they train on is no longer generated by humans but by other AI? If a generative adversarial network produces a synthetic text or a synthetic image, and a natural language processor or a CNN trains on that synthetic data to learn how to interact with us, what is the end result of that feedback loop? Will these systems eventually understand human nuances better, or will they slowly, iteratively drift into an alien intelligence, operating on a logic we can no longer interpret or control? Keep questioning the data around you and look closely at the systems silently making decisions on your behalf. Thank you for joining us on this deep dive.